Welcome to qnawire.
And finally, let's see here. We're going to look at the determine the efficiency against extraction pressures. So these extraction pressures of various megapascals. So we're going to go from half a megapascal to 12.5 megapascals. Um, I I just plotted. They gave us the specific values to look at, but I just made a loop and went through a bunch of them. And so where the effect of the extraction pressure on the performance of a regenerative Rankine cycle. Okay, so here we have this this case here where we basically bleed some off, go through here, and then um, basically have a regeneration process here, as opposed to a reheat process. So we're bleeding off, and then taking this at a certain pressure, and then coming out here to essentially help with getting the feedwater up, feedwater temperature up by mixing things here. All right, so what do we have here? Let's see here. Is there anything else I wanted to say about this process? I don't think so. Again, we're just looking at extraction pressure here. So the extraction pressure, is here. I didn't put labels on these things, I guess. Let's see here. This is 5, 6, 7. 1 and 2 are basically at the same point here. 3 and 4 are essentially at the same point here. So we have two pumps, and I think these are both kilojoules. Oop, I don't want to erase. Kilojoules, if I can squeeze that in there. All right, so what happens here? As the bleed pressure goes up, you can see the efficiency, well, it goes up a little bit, up a little bit, up a little more, and then it starts to drop. Right? Net power basically just continues to decrease. I looked at the saturation values here and here, and in the case here at the bleed, we're at these low pressures, we're at two-phase, and the higher pressures, we're in supercritical vapor. And at the turbine outlet, we're basically it stays constant because this point here isn't changing as we move this line up and down. All right, heat transfer in, heat transfer out, pump work. Okay, so we got two pumps, one after the feed water heater, one before, and then the work out from the turbine. Okay, so we can see here that these pump pressures, one goes up, one goes down, okay, which isn't surprising if you just think about it a little bit. But again, they're very small changes off of this power out of the turbine. So let's see how these things look. Network, as this pressure goes up, we just continue to go down. And again, I think this would actually go to 0 if we just continued. Basically, we bled everything off, and we just didn't go anything through the turbine, which would be a silly, stupid thing to do. But so as that get up to, what was it, 15? I think we used 15. The high pressure side, I think was at 15 megapascals. Let me look at my code. Yeah, 15 megapascals. That looks about right. So the efficiency, interestingly, has this little peak here, right? And then it drops. Although you can see here that the efficiency doesn't change a whole lot. This isn't a wide range here. And this peak is kind of, I mean, it's all pretty good up here. So, we really want to be at a low pressure here, coming off of this regenerative cycle here. Since this quality factor doesn't change at all, I just plotted this one here. And we can see here, all except for this very low pressures here, or yeah, low pressure here, way down. We are at in supercritical. So again, we saw that just these two at these low pressures here. And then I can't remember what did we use for the condenser? 10 kilopascals. So this was 15 megapascals, and this was 10 kilopascals. All right. So again, we can see here just how things change. We want to be kind of in these low ranges here, like down where basically this is just getting very close to being where it's critical right here. So that would be the kind of an optimal case probably here, somewhere there. I think that's about everything I can think about to say for this.